Hi everyone, today's speaker is our own Stephan Rabanser, who many or most of you know. He is a postdoctoral fellow working with Matt Salganik and myself. He previously did his PhD at the University of Toronto and the Vector Institute, where he looked at questions such as calibration, uncertainty quantification, and selective prediction in AI and machine learning models. And what that means basically is, can we get these models to say when they don't know instead of plowing ahead and outputting whatever answer? And more recently, we've been looking at similar questions with a team of collaborators in the context of AI agents. And this is work that we've just finished the first draft of. Other than the team of authors, you're going to be the first to hear about it. And I think the work will really benefit from your feedback. Before turning it over to him, let me just say a word or two about why I find this line of inquiry to be very exciting. One of the most confusing things in the AI discourse broadly right now is that, on the one hand, these AI agents are blowing past every capability benchmark that people are constructing to throw at these things, including some in our own team in our past work. But on the other hand, except for a very few sectors like software engineering, when people try to use these agents to do real stuff, the uptake doesn't seem to be that high. So what is the reason for this big disconnect? That's what a lot of people are wondering about. One narrative is that, oh, it's just people don't know how to use these things properly, and the early adopters are using it. People are going to pick up on it later. Maybe there's some truth to that. But maybe, on the other hand, maybe the way that the whole AI industry is measuring capability is missing certain important aspects of how agents might fail in the real world, and we need fundamentally new measurements if we are to identify and remedy what those real-world barriers might be. So that's the broader context for this line of research. Over to you, Stephan.
Thanks a lot, Arvin, for the very nice introduction. I guess that already explains a lot of the motivation, but I'm still going to sort of go into a little bit more detail on sort of why we think this is a worthwhile area of study. So as Arvind already explained, this is like the first iteration of this work, so definitely still considered work in progress. Feedback is very much welcome, and you're the first ones to hear about this today. So I'm going to start with a little bit of a motivation exactly on what Arvind just mentioned on sort of the distinguishing sort of factors between capability and reliability. So the dream that I think a lot of us have started out with growing up as kids and sort of like learning about all these sci-fi stories from different directors and novelists, we have always imagined AI as essentially like a reliable and helpful companion in the grand scheme of things. So I think a lot of you are probably familiar with some of these examples from sci-fi, meaning like the HAL 9000 assistant, Jarvis from Iron Man, or also Samantha from the movie Her. And there's a lot of like really nice qualities that these assistants have. They manage like an entire spacecraft autonomously. They're like a personal AI that sort of manage tools and plans and sort of execute actions. Or they're also sometimes conversational assistants with deep contextual understanding. And so I think the shared vision behind a lot of these tools is essentially that we have some notion of artificial intelligence that understands, acts, and hopefully can be trusted in a lot of settings. And the key enabler that we have sort of like settled on as of now in this field is essentially to rely on some notion of a large language model and sort of like making sure that we build additional infrastructure on these language models to make them sort of achieve this sort of level of automation, essentially. Now, I assume a lot of you are familiar with what a large language model is. They're essentially neural networks that are trained on like huge text corpora that are essentially trained to predict the next word in a given sequence. And these are essentially special because they have a huge amount of parameters that go into them. They're trained on essentially internet scale data. They possess the capability of essentially being very generalized in terms of handling a lot of different tasks like translation, coding, reasoning, summarization. They're able to, in context, adapt to a lot of different use cases instead of having to retrain a model. So they can easily adapt to new tasks from just a few examples. And they are pretty good at instruction following these days, especially the frontier models in terms of being aligned with like and following human intent. And what is an AI agent essentially, or an LLM-based agent? It is typically an additional sort of like set of scaffolding tools around this central tool, which is the LLM. And so it essentially wraps the LLM in this sort of action loop where what the LLM essentially does, it essentially receives a task description, and then the LLM tries to reason about what to do next, acts on the environment using tool and environment executions, then essentially observes what it just saw, and then iterates in this in multiple loops, and then at some point returns with a final response. And so essentially the LLM can essentially be thought of as essentially sort of this planner and this reasoner in the middle, and then there's additional sort of scaffolding and context around the LLM, which allows it to essentially be perceived as an agent. Now, recently we have seen a lot of these agents essentially moving from research prototypes into actual sort of deployed products. And so probably a lot of you have sort of used tools like Cursor, GitHub Copilot, or Cloud Code in some way, shape, or form. So these are most notably coding assistants. Then maybe some of you have also used some of those web agents like OpenAI Operator or Google's Project Mariner. And recently we have also seen the launch from a lot of tools from Anthropic on computer use, as well as sort of their co-working assistant, which can sort of do similar things as Cloud Code, just with a slightly different sort of sprinkle on top. Now, the promise with a lot of these sort of agents is substantial. Like if they were to be able to actually perform their tasks reliably and dependably, the impact would be very transformative in a lot of different fields. Now, I have a few examples here. There's lots more. The examples that I'm listing here, for instance, are being a computer scientist myself, of course, like software engineering is like very tangible, especially with the emergence of Cloud Code, of like autonomously sort of writing code, fixing bugs, testing, maintenance, stuff like that. It could even lead to like huge amounts of automation where we don't even have any sort of humans at all anymore in terms of like industrial processes where we have unattended quality assurance, scheduling, process optimization, or in science, if it worked well and reliably, it could automate like literature reviews, data analysis, and probably also reproducibility of scientific results in the grand scheme of things. But yeah, as Arvind already mentioned, there's definitely this bottleneck between sort of capability and reliability, right? We see that capability is not necessarily the issue right now. These models, they are like getting increasingly more capable, but at the same time, the question of whether we can trust them has not really been solved. And in a lot of cases, these models are perceived to be very brittle under like actual real world usage, essentially. And so I guess what I wanted to sort of highlight here is a bunch of those failures where we have seen like very prominently that these AI agents are just not ready at this point in order to be deployed. So there's a famous example from the OpenAI Operator web agent, which essentially made at some point an unauthorized purchase from Instacart, despite sort of the user telling them that they're not allowed to do this, so essentially bypassing like user default safeguards, essentially. There's another example from New York City where they launched a chatbot on the website that gave illegal advice to landlords and all of them incorrect answers to journalists asking the same question afterwards in order to audit the tool. And then probably my favorite example, the replicated AI agent just basically deleted an entire production database, despite explicit sort of instructions in its instructions forbidding such destructive operations and such drastic changes. And so what is striking is that a lot of these agents, they were essentially thought, based on the internal audits, to be reasonably sort of capable in terms of what they should do, and so they were launched anyways, despite sort of maybe better judgment of reliability issues that should have been addressed before launching them. Now you might wonder, okay, if these tools are launched, sort of what is the typical evaluation pipeline? How do people know if the agent is good or not that they're trying to launch? And so the way that this typically works is these evaluations, they start with a benchmark, and the benchmark essentially has a bunch of tasks within it, so different sort of individual sort of items we ask the agent to do and individual tasks that we evaluate the agent on. So we essentially, when we want to launch our new agent as a company, we basically feed all of these tasks into the agent, and then we look at, did the agent get any of these tasks right or wrong? And then we essentially build some aggregate measure of that performance, which usually is some notion of accuracy. And then we sort of like go onto our leaderboard and we just rank it on a leaderboard, and we just sort of like pick the agent, I guess, that performs the best on any given leaderboard. And that's a typical practice that is just easy to do, it's scalable, it's easy to understand. But the issue is that this practice alone, sort of just compressing all of that into just a single accuracy number, the entire agent behavior, is maybe not a great idea. So this hides a lot of very crucial and important information, we argue. So it doesn't answer, for instance, the question of would the agent succeed again on the same task, or did it just get lucky by solving it in this particular instance? What if inputs were to change slightly? Would the agent still be able to understand what happens? Does the agent know when it's wrong? This is very much related to some of my past research that I've done in my PhD. And if it fails, how bad are these failures in the first place? Are they catastrophic? Are they just very benign? Sort of what is the notion? What is the nature of these failures? And so I want to do a quick sort of experiment with you guys on sort of one of these dimensions that we're interested in of evaluation. I have two agents. I have agent A, which always solves the same 70% of tasks, and it always fails on the remaining 30% of the tasks. And then I have an agent B, which solves each task with a base probability of 70%. Show of hands, which agents do you prefer? Agent A, who prefers agent A? Okay, show of hands, who prefers agent B? Nobody prefers agent B. Very good. This is exactly what I wanted to see. So it seems like you're all still with me and paying attention. That's good. Yeah, agent A essentially is preferable. Why? Because it is predictable. We can understand on which part of the task it fails, and this allows us to sort of debug it and improve it. Whereas on the other side, agent B, it fails like basically randomly. It's really hard to get a sense of sort of when the agent fails and what sort of leads to these failures, and so debugging is increasingly harder. And if you just look at accuracy, these agents have the same accuracy. So it's really hard to sort of disentangle sort of the deeper behavior from just that accuracy number, if that's all that is available. And so in this work, what we're interested in is essentially sort of go beyond sort of the current evaluation practice of just reporting mean task success rate, or sometimes even not even that, just like user preference ranking, to sort of a multidimensional evaluation of sort of how does the agent behave in terms of reliability properties. And so this, of course, leads to the question of how should we evaluate this? How should we define it in the first place? And the approach that we've taken as part of this work is to essentially take a step back and take a look at some classical safety critical engineering disciplines and how they approach reliability, and sort of take inspiration from that and try to bring it into the age of AI agents. And so this is where I'm now going to briefly talk about sort of this cross-dimensional idea that we have for reliability. So I guess a lot of you have used sort of systems or tools where safety is inherently important, especially traditional, very engineering-heavy disciplines really rely on a lot of sort of different notions of reliability. I'll have an example here for aviation. As we all know, air travel is pretty safe. Of course, sometimes accidents can happen, but still in the grand scheme of things, it's one of the safest ways that we can travel. And this industry has essentially built a lot of tooling, a lot of sort of policies, a lot of checks, a lot of standards around sort of wanting to make sure that air travel is safe. And so there's ideas like deterministic execution, sort of shielding flight critical software, redundancy in multiple levels. We have another discipline in automotive where essentially we sort of have sensor fault testing, we look at edge cases, we have functional approaches to safety. In nuclear power, for instance, there's very explicit like failure mode modeling, assessing probabilistic risks and sort of like tail events. There's like multiple layers of defense typically in place in order to make sure that they work safely. And then in industry, where we have sort of a lot of automation sort of picking up these days, there's also a lot of ideas like deviation monitoring, sort of process alarms, safe shutdown procedures. These are all ideas that sort of have made sure that these industries, in the grand scheme of things, even though of course accidents always happen, have sort of increased the standard that we can expect for reliability. Now, in each of those fields, reliability is not the same as capability, right? So if I have a car that has like a really powerful engine, if every time I start the car, it sort of sometimes starts, sometimes it doesn't start, but when it starts, it works well, that's not reliable, right? I want the car to start every morning if I want to go to work. So these are two different notions. Now, maybe as you've already seen, there's a lot of terms that I'm putting up here that are not necessarily just exclusive to one of these domains. So for instance, like multiple layers of defenses or sort of redundancy by design are definitely applicable to many of these industries. And so we wanted to take a step back and understand what are the actual unifying principles in terms of reliability when it comes to all of these domains that we've looked at. And what we were able to find is essentially 4 unifying principles that overall seem to address or sort of be the source of the reliability that we expect in these systems. The first of them being consistency. What we mean by consistency is essentially that a system must produce repeatable behavior under nominal conditions when we sort of query it multiple times, right? When I start the car, it should always start. Then we have the other metric, which we call robustness, which means that under slight perturbations, systems should degrade gracefully, and they shouldn't just sort of outright fail. So there should be like a gradual degradation process in terms of how strong of a perturbation or change is applied. It should sort of degrade gracefully. The third one is predictability. This is related to the uncertainty quantification that Arvin mentioned at the start. So systems should ideally know when they are essentially deployed beyond their means and when they don't know something, and not just like spit out something if they're sort of asked for it. And then the last one being safety. Not all failures are equal. It really matters sort of what kind of failure modes we see, and the severity of all of these matter. And these are the unifying principles that we sort of have extracted from all of the sort of the study on sort of the cross-disciplinary study of reliability. And now I'm going to talk about sort of how we are planning on bringing these to the field of AI agents and sort of like instantiating this framework in more detail with like more explicit metrics or more specific things that we care about for AI agents. I'm going to start with consistency. Again, the idea here is that if we have a benchmark and we have a task in that benchmark and I run that task k times, I want to understand how similar are the runs that I get. And ideally, the agent does the same thing every single time. So the first one, outcome consistency, if I just sort of take that task execution k times and I look at what did the agent do, did it succeed or did it fail on a given task, I sort of want to measure sort of how consistent is that. The other notion of consistency we're interested in is trajectory consistency, where we have two subtypes of, where basically we're interested in if we take a look at the intermediate steps that the agent is taking as it is executing its tasks or its tool calls. Then I want to understand, does it usually have the same type of actions across all of these executions? And does it also have the same order in terms of how it calls individual tools, for instance? And then the last one that I have here is resource consistency, which means that if I run the agent multiple times, does it sometimes cost me, I don't know, $10 to run the agent? Or does it sometimes cost me $1,000 to run the agent on just the same task again? This is important, it's the same task. Let's take a look at some of these in more detail. So if you remember agent A and agent B from before, they had widely different reliability profiles in terms of their consistency. So in this case, agent A is again the agent that essentially on any given task, which are the rows for all of the different runs that I have, succeeds very deterministically, right? So for the first row, for the first task, we see that every single time I run it, for every single run, it always succeeds. And for the last one, we see that it always fails, essentially, right? So this is a pretty consistent agent in terms of how it approaches how it can solve tasks. And then we have agent B, which again has the same accuracy in this setting. They both have 60% accuracy, which sometimes succeeds on a task, but sometimes it doesn't, right? With the exact same inputs. And so I won't have too many equations, so don't worry about this. Basically, the idea is that we want to sort of compute some notion of variance essentially over all of these runs, right? So if there's a lot of variance in terms of whether the agent succeeds in any given run, that's bad. And if there's a lot of consistency, that's good. And so we sort of map this to like a number between 0 and 1 in terms of quantifying how consistent is the agent. The other notion of consistency I talked about was trajectory consistency, where in this case, let's assume the agent first goes in run 1 and then basically searches something, then reads a given piece of text, then writes some code, then searches again. And then in the second run, maybe, again, on exactly the same task, it might do 2 searches, then go on to read some piece of text and then write some code. Then we can quantify sort of how different is that in terms of the distribution of tasks. And so in this case, we see that there's like a slight sorry, in this case, if we compute this, we actually see that distributionally it's sort of the same, right? I mean, there's 2 searches, there's 1 read, and there's 1 code in each of these. Then when we take a look at sort of how sequentially consistent this is agent, meaning does it always execute the same things in the same order, we see that it is not very sequentially consistent, right? I mean, the 2 searches at the start, they're the same if we were to actually take a look at the exact sort of appearances of each of these given tool calls, but it is not necessarily in terms of the exact execution order because afterwards they basically differ. So the first one asks, are the same tool types used? And then the second one is sort of like, when are the actual actions being taken? The last one that I mentioned was research consistency. Yeah, if I have an agent that basically always predictably almost always exactly returns with the same cost amount, then that's good. But if sometimes it takes me like $10 or sometimes $1,000 to run the same task, that's a problem, right? If there's this much variability. And so resource consistency can be measured with respect to a bunch of different notions that we're interested in. We can pick cost, we can pick time, we can pick sort of the number of API calls that are being made, or sort of the exact sort of tool use cases that we have. So this is the resource consistency part. The other broad notion that I had was robustness, right? Which essentially measures how does my performance profile degrade if I change maybe the inputs into the system slightly. And so let's assume that I have a set of baseline tasks for which my accuracy was 80%. Then if I inject sort of artificially a certain amount of faults into the tool calling process artificially, then we want to measure sort of can the agent recover from these tool failures. So basically, if I say sometimes the agent has I don't know, like the website is unavailable from which it is trying to fetch something, then if it tries again, maybe after some time, maybe it was just a temporary problem, and it can fetch from that website again. Structural changes. So basically what happens if I slightly change the way that a certain data format is returned from a database. If it is sort of still conceivable from the data format, what it says, and it's still somewhat semantically consistent, then the agent shouldn't degrade in terms of accuracy meaningfully, because then it means it might sort of like just overfit explicitly to the particular structure that was in the original problem formulation. And then the last one, prompt rephrasing. So if I rephrase the prompt that I give to the model slightly, but semantically still being the same, sort of how much degradation do we see in these models based off of just that? And we measure this essentially as a clamped sort of ratio between sort of how bad is the accuracy that we get after applying the changes compared to the baseline that we had, which was in this case 80%. Yeah, for the fault robustness, meaning sort of how easily can it recover from tool calls, let's again take a look at an agent here. It calls an API multiple times. The two first ones are okay, but then suddenly there's a timeout, or there's like an error of 500 from the server. And so what we do, we essentially artificially inject a certain percentage of tool call failures into this chain, and then observe, does the agent recover from these? And so some of the failures we have here are API timeouts, certain HTTP errors, malformed tool responses, or completely empty responses. Does the agent understand what happened there, and can it sort of recover from these settings? That's sort of one thing that we study here. For structural robustness, we're interested in if we're given the specific format of JSON from an API, for instance. If I reorder the keys, that should not do anything, right? If I just reorder sort of at which level a given item appears, that shouldn't really change the thing, sort of the outcome in any meaningful way, shape, or form. What if I change the date in format in some way, shape, or form? Does that do anything? Or what if I change the format in a more meaningful way, where basically suddenly items are no longer listed sort of as lists using square brackets, but they're just listed as a comma separated list? Or I have essentially the amount now with a $ in front of that. Does that change anything? So we look at all of these perturbations, where essentially the idea is to have the same semantic content, just a different sort of surface level structure. And then we take a look at what happens. And the final one for robustness was prompt robustness. So if I have an original prompt, which was about finding the population of France according to census data, then this might succeed. But if I have like a bunch of like reformulations of the same prompt, does that do anything? And so one thing that we also do explicitly was to sort of inject more sort of like colloquial text into how the model needs to respond. Because I think a lot of users, when they talk to these models, they don't always like write very nice English. Sometimes they write it sort of like as in, well, you should sort of get from what I'm writing here as if I were to talk to a friend, but I can extract the right answer, which might also have typos and stuff like that. And so in this case, we see in this, like, for a typical example, maybe the agent would fail on this particular one, but it wouldn't necessarily fail on the other rephrasings. And so what we do here is we, again, generate multiple semantically coherent rephrasings where sometimes you have more aggressive, sometimes less aggressive sort of changes to the way the prompt is phrased. The third dimension that we had was predictability. And this is central to, can the agent understand when it is likely to not succeed? So we're given a task, we give it to the agent, and we get an answer from that. And ideally, we don't just get an answer. Ideally, we get some notion of confidence from the model. So the model tells us, I am, in this case, 85% sure that the response that I just gave you is correct. Then given that number, we might want to do some selective automation where essentially we can say, well, if my confidence sort of exceeds a certain threshold level, then I say, okay, we can just like completely go ahead with that answer that the model just gave. Otherwise, we might have to flag it and sort of like bring in a human to actually review what exactly happened in this particular prediction and sort of audit it in some way, shape, or form. Now, when it comes to this overall pipeline, there's two key quantities of interest that we're interested in. The first of them being calibration. What does calibration mean? Calibration is essentially the desirable property of having probability grounded in base frequencies, essentially. Probabilities should mean what they mean. So if I say it is going to rain with 80% probability, then in 80% of those cases where I said it is going to rain with 80% probability, it should have rained in 80% of those cases. So it should match that base frequency. And so a model that essentially aligns confidence and accuracy, being on that diagonal line, that is a model that we call calibrated. Now, usually what we see in most of these models is some notion of overconfidence. So basically what we see is that there's a significant gap between sort of the confidence and the accuracy of the model, where the confidence is typically a lot higher than the warranted ground truth accuracy that we get from these models. And so the way that we measure this is using a very standard notion called expected calibration error, which essentially computes sort of this gap over all of these different sort of bin categories that we have here, where we essentially group a bunch of confidence levels together into these bins. The other notion of predictability that we're interested in is discrimination. So essentially, if I were to take all the like the set of answers that the model gave for correct decisions that it made and for incorrect decisions that it made, if I then look at the confidence that it assigned to both of these groups, then there should be a clear distinction between those two groups. So if I say I have low confidence, then it is most likely a failure. If I have high confidence, then it is most likely a success. And so ideally, a model with good discrimination properties should have like a very distinct sort of profile of having failures on one side and successes on the other side of confidence. Now, a lot of models, they're not very good at this. What they essentially do is they have a decent degree of overlap between these two distributions here, where essentially it is really hard to tell for especially sort of these middle confidence numbers whether the model should be trusted or it should not be trusted. So this would be an example of poor discrimination. And so the way that we measure this is essentially using a metric that sort of assesses how good the ranking quality of those scores are, which is the AU-ROC metric. The last category that I mentioned was safety. And so not all failures are created equal. It is important in safety to measure how bad things are. And so what we came up with here is essentially this graded scale from 0 to 1, where we have minor, moderate, and critical failures. And so I'm going to give you some examples as to what we might sort of quantify as a minor, moderate, or critical failure. So if there's like a formatting error, essentially, that the model makes, then maybe that is not that much of a concern to the downstream application. Maybe the model makes a few unnecessary edits, which make it a bit harder to trace sort of why these edits had to be made in the first place. So this might be a more serious issue. One thing that we saw in some of our examples was essentially like an incorrect charge maybe to our credit card or something like that. This is definitely more critical. And then maybe like in the Replit AI agent example case where it essentially deletes the entire production database, that is probably very bad as well, right? So that is definitely on the higher end of criticality. And so the key notion to understand here is that it's not necessarily sort of like about an aggregate number in this case, but it's more about sort of understanding these exact tail behaviors. So doing a more critical study on when do these things actually happen, and not just sort of like blindly trusting an agent that 99% of the time is like fail-safe, but if it sort of like fails catastrophically 1% of the time, that's still pretty bad. The way that we do this is we take a look at the agent logs, and we extract essentially from these agent logs, if there was like a meaningful violation that happened in any way, shape, or form. So in this case, let's take a look at sort of this sort of like banking agent, which allows you to sort of do a transaction from A to B. Then I might ask the agent to do this for me, then it might have to ask for my credentials, and then it might sort of like do a tool call to verify my credentials, and then it might transfer like 10 times the amount suddenly. Of course, like this is a very on-the-nose example, but I guess it's meant to be like that. What we then do is we sort of take a lot of these logs, we put them through essentially an LLM judge, and then we take a look at which of the categories that we're interested in did it fail on. So in this case, it didn't really expose any personally identifiable information. It didn't perform a destructive operation necessarily, but there was this incorrect amount that was charged essentially to account A and sort of like credited to account B. And so we found in this case, if you take a look at the transcript, that there's one violation out of all of the categories that we have defined. And then, of course, afterwards, once we sort of have these compliance results, we go in and we have like a grading system which tells us sort of based on how many of these violations we saw, how much of a severity is this actually in terms of the overall violation. So again, if it were to be like malformated responses or anything along these lines, it would be a pretty low severity score. But yeah, charging an incorrect amount is a pretty severe is a pretty severe issue. So this would be graded as a probably pretty severe instance. Now, in terms of what we are overall interested in terms of like aggregating our results, we combine consistency, robustness, predictability into one overall reliability score as well, even though we also look at them in detail. But we have some trend plots that sort of like look at the overall trend as well. So this is what I wanted to briefly mention here. Safety we report separately because it is inherently a tail phenomenon. So we don't think it makes sense to sort of like average this into any of the other scores necessarily. One key design principle that we wanted to go for here was to essentially make sure that accuracy and reliability are disentangled from each other, because in a lot of cases it is really hard to sort of otherwise track if these are like actually distinct notions that we should track in the first place, or whether just tracking accuracy from the first place would be sufficient in order to understand whether reliability would correlate with it in any meaningful way. Okay, I have some empirical insights for you as well. So this was basically just setting up sort of the framework behind it. We did two experiments, or two sets of experiments on two complementary benchmarks. We have the Gaia benchmark and we have the Taubench airline benchmark. The Gaia benchmark is a general AI assistant benchmark, which is comprised of 165 tasks on 3 different difficulty levels. And what we need to do is essentially browse the web to find something, do like some rudimentary file manipulation, but then on level 3, which is the harder tasks, also some multi-step reasoning. The way that these are graded is usually using like an exact match grading process. And then what this overall tests for this benchmark is essentially reasoning under a decent degree of complexity. In Taubench Airline, we have a customer service interaction simulation where basically we have 50 tasks where the agent is tasked with assisting a user model to sort of rebook flights, cancel flights, sort of assist them with their booking procedures, essentially. And these are definitely more consequential in terms of the actions, because you need to like issue refunds potentially, or like actually perform a cancellation, stuff like that. And so what this test is essentially a lot of making sure that the agent can use these tools that it is given to, as well as if it has this degree of policy compliance that we're looking for. Now, this is figure 1 in the paper, which basically looks at the aggregate of reliability over model release dates, as well as sort of how it relates to accuracy. What we see on the top is the results that we have for Gaia, and on the bottom, the results for Taubench. And we benchmarked a bunch of different models from OpenAI, Google, and Anthropic, and then we essentially compute a trend line over the overall reliability score, which once again is the aggregate of the first 3 reliability metrics that I mentioned. And so what we see here is that despite these 18 months of releases, reliability has barely budged, essentially, in terms of the overall aggregate measure. This is a sort of industry-wide phenomenon. A lot of providers essentially have the same profile, so it's not necessarily that one provider is ahead of the other ones in terms of this notion of reliability that we measure. We also see that there is a slight uptick in terms of sort of increase in accuracy and increase in reliability correlating with each other, but it's still not a very strong sort of upward trend at this point. So the overall trend is reliability has not really moved significantly. We then go in a little bit deeper and study sort of each of these dimensions in more detail to understand if there's like any interesting findings with respect to each of these dimensions in particular. And what we first looked at was consistency, and once again, I have like some plots here where we can see Gaia on top, Taubench at the bottom, and in this case, I'm specifically looking at outcome consistency. And what we can see is that a lot of these models are not necessarily very outcome consistent. So once again, this measures for the same task. Does it give me the same answer every single time that I run it? Not necessarily in terms of like the intermediate steps, but in terms of the final response that the model makes. And in a lot of cases, this outcome consistency is not very high, where again, 1 would mean it always gives the same answer, 0 means it's super unreliable in terms of what answer it gives. So they often fail to do this consistently. And what this essentially shows is a gap between the pass at k number, which is one that is often reported in a lot of agentic benchmarks, which means that if I try to solve a task k times, if it succeeds at least one out of those k times, I say this is a success. I count it as a success. Whereas the pass to the k measures, do I succeed every single time I measure? I sort of like try this task. And so this sort of like shows a meaningful discrepancy between these two ways of evaluating the agent. I don't have plots for this, but in general, what we see when we look at the trajectory consistency is that the agent is usually more consistent at selecting similar action types. So distributionally, these agents are more consistent than they are in terms of execution order. So there's a lot more variance in terms of when they pick to call certain tools or when they try to execute certain pieces of their like reasoning chain. In terms of research consistency, we found as well that there's a lot of variability, especially on Gaia. There's a huge amount of variability. Robustness, we interestingly saw that for 2 out of the 3 robustness categories, there is a certain degree of ceiling effect happening, where essentially a lot of the models are doing pretty well for fault and structural robustness. Having said that, this might be due to the so far limited nature of perturbations that we are injecting into these models, and maybe if there's a more sophisticated way of simulating these perturbations, we could actually see that the ceiling effects have not quite been reached yet. Where we do see a fair amount of variation is in prompt robustness, where we essentially see that varying these prompts leads to a substantial amount of variability, but that recent models have especially improved on this particular dimension. So that is also something we see. So if you look here essentially at sort of these improvements from like a simple model like 3.5 haiku and sort of the step all the way to 4.5 opus, we definitely see a decent amount of improvement in this particular dimension. Predictability, which once again was mostly about calibration and discrimination. In general, what we found, if we look at the numbers, is that this is usually the category that a lot of these agents typically struggle with the most. So to really understand when they encounter something that they don't know. We do see some recent improvements on a lot of these benchmarks, especially on the TauBench suite of tasks. We see that there's a lot of improvement. But it's still not at a level where we would say that the models are necessarily doing very well at this particular task. So especially calibration and discrimination are a big problem still for these models. We also did a more detailed safety analysis for TauBench in particular, where we sort of went in and looked at the failure types that we saw when we take a look at sort of the transcripts that we get from these models. And in a lot of the cases, we see that especially sort of the older models, they're very bad at this. They often charge like hugely like wrong amounts to users in terms of like rebooking fees and stuff like that. So financial accuracy is definitely a big issue for especially older models. This has significantly improved though in the more recent models. They are a lot better at sort of like following these particular instructions of sort of like doing calculations correctly and sort of like not circumventing any policy that is being put into the prompt. But at the same time, even the most recent models still have some of these failures. And so even infrequent high severity failures are a problem, and we should take them seriously. So even the latest models have not completely solved this. Okay, I'm almost at the end. I wanted to sort of like briefly recap some of the main takeaways. Reliability and accuracy, not the same thing, and agents with very similar accuracy can have widely different reliability profiles. This is something that we have seen in our research. Reliability does not improve at the same pace as capability, and these 18 months of progress that we measured, we saw a fair bit of improvement in terms of accuracy, but not by all means the same improvement in terms of reliability, and this is something that we observe industry-wide. Predictability and consistency are a bit of a problem, predictability being the weakest dimension out of all of them so far. Agents are often poorly calibrated and cannot reliably signal when they don't know something. We also looked at scale in particular. It is usually true that the larger models seem to improve in the grand scheme of things, but they don't necessarily help, and this is something we found interesting with consistency. So often the larger models are more inconsistent in terms of how they come up with their responses. And yeah, I guess sort of overall, taking a step back, this cross-dimensional sort of like grounding in terms of what things to measure is important in order to get this full reliability picture of the agent. I guess this I can probably talk about in case people are interested. I think in the interest of time, I wanted to make sure that people still can ask questions. I will briefly talk about the limitations. Of course, for now, we only have 2 benchmarks. It's a pretty narrow slice. We hope to expand on this more in the coming weeks. We only use a single scaffold for each and every single benchmark, so there's also some scaffolding effects that we haven't yet taken into account. The metrics themselves, we think we did a good job at formalizing them, but having said that, there's probably other decompositions available that measure similar things that we're interested in, so this might not be the only decomposition that we're proposing here. And then maybe some of you have already noticed this, yeah, we are using an LLM as a judge in order to come up with sort of like scanning the transcripts for safety violations, which in and of itself might be unreliable, but it is one of the only ways that we can do this at scale right now. We have a bunch of interesting future extensions that I can talk about if you're interested. But I guess I wanted to close here now by just saying, yeah, we should sort of move on from this sort of like very raw notion of how often does the agent succeed, and instead ask sort of how predictably, consistently, robustly, and safely does the agent behave. So this is hopefully the closing thought and takeaway message that you can get from this talk. And yeah, that's it. Happy to take any questions.
Hi, thank you for the amazing talk. I think I understood all of it, which is
excellent.
Great.
Happy to hear.
So I was thinking, so LLMs are sort of like centrally the key part of any agentic system, right? And inherently, these LLMs are probabilistic systems. Meaning, so when you try to measure consistency, which is sort of like either trajectory consistency or whether they'll be behaving the same way if the tool call fails, that's all sort of decided by a probabilistic system in the backend. So converging towards, I guess, like 100% consistency, is that even like a good goal? Like, is that even achievable in any sense, or do we need some sort of like a deterministic layer in between, instead of just relying on these LLM-centric agentic systems?
Yeah, it is possible that there is a certain degree of changes that need to happen more fundamentally that sort of are wrapped around sort of the probabilistic system underneath it. I'll say one thing. We did all of these experiments with temperature zero, meaning the agent or the LLM samples deterministically, essentially. So any sort of variation that you get are essentially based on like other sort of like, I don't know, like other sources of noise that you essentially have in the system, not necessarily from the sampling procedure. Yeah, there probably is a need for like either what you propose, sort of like putting an additional system around it, or maybe a more clever way of fine-tuning the model at a certain stage once you want to deploy it in a more safety-critical scenario. I think right now, a lot of these ways that these models are trained, and these models are fine-tuned in particular, is actually to encourage diversity in their answers, which is a lot what the reinforcement learning fine-tuning procedures are supposed to do. And so we're thinking about, we have not like really formalized this just yet in detail, but we're thinking about what this would mean in terms of having maybe that initial stage of RLHF, of fine-tuning, essentially making sure that the model explores like diverse sort of a diverse solution space, but then having an additional tuning phase on top, which sort of clamps the model down into like actually being sort of encouraging more predictable behavior and more consistent behavior, essentially along the line. So I think this is definitely not something that the field has necessarily sort of agreed upon just yet, what the right way of doing this is, but we still think in a reliability critical system, it is important to sort of get that same answer. Like if I asked, in this case, like let's take the tau bench example, to sort of cancel my reservation and sort of like transfer the amount back, I want that to happen very deterministically, right? So we still think it is a desirable goal in terms of how we get there. I think that's a bit more unclear, and there's certainly room for research in this space, yeah. Kara?
Thank you for the talk, it's super cool. I have two questions, both about like the sort of notion of a task. So first I was wondering is like, how do you decide when things are similar enough to count as one task versus when like they are separate tasks? So like buying a book versus buying a specific kind of book, for example. And then the second question is about how you're thinking about the distribution over tasks, which I think would affect like your calibration measurements. So like, if a model says that, or if a model is like judged to be overconfident by a calibration measure, like one interpretation is that it's like overinflating its probability of success, but the other is that maybe it just thinks that tasks that it's more likely to succeed at are more common than like the distribution that you're evaluating calibration perspective. So
yeah, what was the first one again?
Just like what counts as a task.
Oh yeah, what counts as a task, exactly. In our experimentation, it was very easy. We basically take established benchmarks, which basically have like tasks defined as single records essentially in the benchmark. So we take a given task from that benchmark, and then we just evaluate on that, and then there's like 50 tasks. We go through each and every single one of them, and then we analyze them afterwards. So I think this is more of a benchmark design question, essentially, in terms of how do you come up with a benchmark that has like a diverse set of tasks that reflects well sort of what you want to cover ultimately. So for us, this distinction was very simple. In terms of what you mentioned with respect to, I guess it is somewhat related to the task difficulty question. So we have some experiments for Gaia with respect to the different levels of difficulty. So in Gaia, you have level 1, level 2, level 3, where essentially level 1 tasks are pretty easy, level 2 tasks are more difficult, and level 3 tasks are pretty involved. We did take a look at how calibration changes across all of these different tasks, if we were to like stratify them by difficulty level. Interestingly, we did not necessarily find that the model sort of is better calibrated on the easier tasks and worse calibrated on the harder tasks. So we actually found it to be pretty generally sort of unsatisfactory in terms of its reliability profile. That was an interesting finding, we thought, yeah. But good question, yeah. I think Max was first, yeah, Max.
Yeah, great talk and slides as expected. I'm always jealous.
Thank you.
So one question I had was in terms of the liability score and the averaging.
Yeah.
It seems like specifically for your consistency metrics, if you're averaging them together, there could be some tension between them. Like the Jensen-Shannon divergence could be maximized in some instances, but the edit distance could be minimized and vice versa. Like in the instance where you're doing the same exact processes, but you're doing a top-down versus a bottom-up procedure, that would say that the model is not that consistent when in reality it's achieving the right goal and it's just doing it different ways. So I wonder how exactly you disentangle that.
Yeah, we think, and so in general, it is always hard to sort of like come up with like a single score for all of the things that we're trying to measure. So basically, the way that we just solved it for now might not be sort of the end game in terms of how the reliability score will look like ultimately. For now, what we do is we just do essentially uniform averaging over all these different quantities. We also didn't want to sort of go in and have an explicit weighting because it's probably application dependent. In some application, you might care more about one specific notion of reliability than the other. Yeah, it's a tricky sort of concept of sort of aggregating all of this into just one number. So I think it's something that we probably can still spend some more time on in terms of like how exactly they should look like. But I think we emphasize in the paper as well, and hopefully I've convinced you here as well, that sort of looking at the individual sort of categories in detail makes a lot of sense, and sort of the aggregate score should be like, it should give like a general sense of direction instead of like actually be the main insight in terms of, oh, this is the actual finding that we had that is very interesting in terms of like a takeaway message. So I hope that makes sense.
Yeah.
Please.
Thank you a lot for that. It was really good to know. I had a question about how you think about the reliability of the LLM as a judge method itself and whether that could impact any of the downstream.
Yeah, so I think we looked a little bit at the results that we got, and we have some other efforts in the other research streams that we have on the team where looking at agent logs and agent transcripts is an inherent part of how we assess like a certain quantity that we want to measure. There are some mistakes sometimes that happen. It depends a little bit on what model do you use. If you use like a state-of-the-art latest model, it is typically pretty good at this task. There are some false positives that you see every once in a while, especially in sort of these customer service interactions where basically the model would think that the agent just canceled the reservation despite the user actually like allowing for that cancellation in the first place, and then sort of counting it towards, oh, this was a destructive action, right? You could just cancel you just cancel the reservation without prior user approval. So I think this is still something that is a big caveat in terms of like the overall takeaways, that the only way to do this at scale right now is to actually use like an automated system that can go through text and go through language, which is a language model. In the grand scheme of things, we did not find a lot of cases where the model sort of missed something critical or sort of misinterpreted something. But having said that, it probably crucially depends on, what model do you use, and you probably need to go in and sort of check some of these yourself, like these if the model like flags a very high severity failure, it would be good to sort of like check those manually. I think that's a good practice. So yeah, I think that's, we had some questions here as well first. Yeah. Matt, do you want to go first?
Yeah, thank you. At the beginning, it seemed like you were talking about real world use cases and moving away from benchmarks. And then what it seemed like was a more sophisticated benchmark. And so I'm wondering how you think about this tension of what it means to measure reliability in the absence of how the thing is used in practice. So for example, you said 747s, airplanes are reliable, but they're not reliable for flying into a hurricane or something. So like, there's like something about reliability and the way the system is being used that are conjoined. It's hard to think of one without the other. So I'm wondering how you think about bridging. So I agree, this is a huge improvement over accuracy, 100% agree. But then how do you think about bridging this into real world uses?
I think ideally we would want to, I guess there's multiple answers here. Like there's one part which is about the evaluation part, which is what we have mostly focused on here. Then there's the other part of what design decisions does that inform, right? Sort of what are the takeaway messages in terms of people that actually build these models, right? How can they make sure that they improve on things? I think in general, it is probably tricky to sort of in general go in and have these systems. I guess, okay, let me take a step back. I think in general, what these benchmarks are ideally supposed to do is to have a reasonably accurate depiction of what you're going to encounter in an actual deployment setting. Mm-hmm. I don't think we're quite there yet in a lot of cases. A lot of these benchmarks, they don't quite measure exactly how these things are going to plan out, but they still give you sort of a sense of directionality. And so I think if we benchmark these systems, that's often the best we can do without having any sort of other explicit access to like proprietary information from a company. Like if a company actually wants to deploy a product, they might have some proprietary information that they're not willing to release, and then sort of like actually working with them in order to getting access to that data, how the system is actually used. There's often barriers in terms of actually getting there. So I think for now, and in terms of reproducibility, we wanted to make sure that we do this essentially on like standardized benchmarks that people are already using in order to measure something that can be reproduced. Having said that, I think in a lot of practical applications, it would be important to really go in and take a look at the actual problems that the people are facing and sort of design benchmarks that are more closely aligned. I think there's a lot of people that are interested in building these benchmarks and or more realistic settings. Like there's a research stream that we're working on which sort of aims to take this a bit further rather than just measuring sort of these agents. Can I talk about the crux stuff? Or?
Sure.
Okay. So basically what we're interested in here in this other line of research that we're currently doing is sort of, is the agent sort of capable of sort of like actually conducting like a very, very end-to-end task, like build an app, submit it to the Apple App Store, for instance. Like this is a very sort of like end-to-end setup where it's not just about like, can it like answer like one isolated web query essentially. So I think there is some interest in moving to benchmarks that are more closely aligned with this goal. But this is still very much a moving target, I guess.
I can give some broader context. Matt, you bring up a very good point. I think you have to study this in the field, so to speak. There's only so much that benchmarks can do. There are other folks doing that. I think it requires, it's human subjects research, requires a complementary set of skills, perhaps more suited to sociologists than to computer scientists. And while there is a lot we're missing here with this approach, there is something that this brings that you can't do with case studies of how people are using models and where things go wrong, which is that you give the industry something to hill climb on. And as we know, essentially all progress in the AI industry is based on maxing on these benchmarks. So to the extent that you can take some of those nuanced insights and bring even a version of that to kind of enhanced benchmarks, the hope is that the next generation of models are going to do better on them.
Yeah, I think I can take one more, and then Gene asked me to wrap up early. Alejandro.
So I was curious about like the safety evaluation part, right? Because one of the examples that you gave is that formatting error might not be as bad, and so we score it low, and something else we score it high, right?
Yeah.
And I assume that for every domain that you care about, you will come up with some rubric, and you will come up with all these scores. But in a way, it also feels like in coming up with that rubric, there's a lot of safety things that you won't be able to necessarily capture, right? There's all these, not only like secondary effects of like a formatting error leading to some sort of catastrophic thing downstream, but you know, a lot, right? Because this is such a big domain. It's not even like just a piece of software that does one task, right, that you formally verify.
Yeah.
So I'm curious, like, in a certain way, how do you think about grabbing this whole domain of possible useful things, assigning some scores, and still having the confidence at the end of the day that the scoring makes sense and that it's not going to result in some terrible things downstream?
Yeah, no, it's a very good question. I think the safety category that we have is probably the most sort of underbaked in general, because we also feel like there's a lot of work in this space where people have really come up with like very interesting ways of like building all of these categories, scoring systems, tracking things over like a long time horizon, as you mentioned. So I don't think we are necessarily pioneering on that front and proposing like necessarily like a new groundbreaking like strategy for how to do safety. We wanted to sort of like insert it into like the broader discussion because we think it is an important contributing factor, but at the same time, we definitely think that sort of the more interesting sort of framework is more in the other dimensions, where we sort of like ask for people to evaluate on all of these other sort of key dimensions of reliability. And this is where most of the contribution comes from. The safety category is sort of for us to understand based on sort of some prior knowledge we had on the team from these like tracing like logs and like analyzing them. If we can sort of like find something that is interesting in terms of like violations that we can think about in these settings, but there's probably a lot more work that would have to go into it in order to really sort of make it safe. And again, this sort of like goes back to the discussion of like, it's hard to sort of like assign like a single score to safety as well. We try to, but in the end, this is probably something that might need a lot of qualitative analysis instead of like a hard quantitative analysis, if that makes sense. I think I have to
All right, thank you, folks.
Thank you.